Hi, Algebra 2. Let's talk about properties of real numbers. Our goals today are to classify real numbers and to use properties of real numbers to evaluate expressions. So first, let's talk about a couple vocab words. You've probably used these, but you might not know these exact words. First, let's talk about natural numbers. They are represented with a capital N if we want to do a shorthand version. These are Count von Count's numbers from Sesame Street. 1, 2, 3, 4. Keep going on forever, but they start at 1. Then our whole numbers is when we have a W representation. These are all the natural numbers and 0. Include 0 with those. All the way on up. Then we have our integers represented by a Z. I think that has something to do with a German word, but I'm not 100% on that. Our integers are these whole numbers and their opposites. So we have -3, -2, -1, 0, 1, 2, 3, all the way on up then. Rational numbers. We represent these with a Q, and the reason is rational numbers have to do with division, fractions, quotients. Therefore, we start that with we start that word with a Q. These are numbers that can be written as a fraction. Specifically, A over B, where A and B are integers. Whole numbers, possibly negative or positive. So some examples of rational numbers could be something easy like 2/3 or -7/2 or +16 all by itself, because we know that any whole number I have or any integer at all, I can just put it over 1 and I have a fraction in the form A over B. Some other numbers that are also included in the rational system are terminating decimals like 0.125 and 7.2. There is a stopping point. And repeating decimals like 1.3333, repeating forever. Or if there's another pattern, maybe it's 7.6262. As long as the 62 repeats, it is a rational number. We are able to write it as a fraction. Now we have irrational numbers, which are numbers that cannot be rational numbers. They can't be written in this form. Numbers that can't be written in the form A over B. So these are numbers with really awkward decimals. Things like pi, things like the square root of 2 or the square root of 3. Any non-repeating, non-ending decimals. Non-repeating and non-ending decimals. So any awkward decimal you have, maybe you have 3.62745, and there really isn't a discernible pattern. Those are irrational numbers. And then, I forgot to write this one on our list, but we need to define the real numbers. Real numbers are all the rational and irrational numbers together. Now hopefully you're noticing that some numbers can exist in each of these classifications. The same number can have different names. So I have a handy graphic that we're going to use to kind of sort these all out. So first I have my natural numbers. That's the smallest piece. But the natural numbers are nested inside of the whole numbers. All of the natural numbers are whole numbers, just like all of the whole numbers are integers. So whole numbers are just the positive versions and 0, but the integers include the negatives. So there are a couple integers out here that are not whole numbers, but all of the whole numbers are integers. They're nested inside. Then I have my rational numbers. I'm going to break to a square here, a rectangle of sorts. My rational numbers. So all of my natural, whole, and integer numbers are rational numbers, but not all rational numbers are integers, for example. Then, other than my rational numbers, I have my irrational numbers. No further classifications within the irrational number system. And when you put all of these together, that's when you have the real numbers, which, by the way, are represented by a capital R. There we go. So with this system in place, I want to figure out how do I classify these numbers. So let's say I ask you to classify the number -23, and I want to know all of the sets that it could belong to. Well, I know that this is a real number, of course, so it's a real number. It's not irrational. I can write it as a nice fraction, therefore it is a rational number. It's a negative whole number, so I know it's also an integer. But because it's negative, I know it's not whole and it's not natural, so -23. Let's talk about the square root of 50. I'm thinking to myself, the square root of 50, I don't know off the top of my head, so I'm going to go to my handy calculator here. Square root of 50, I see is a really awkward decimal. No discernible pattern, so I'm thinking this is an irrational number, which means it is also real. Last one, let's talk about -4/9. How would you classify that? We see that it is a nice fraction, integer, -4 over an integer 9, so this is definitely a rational number, and therefore it's also a real number. But because it is a fraction, not a whole number, it's not an integer, it's not whole, it's not natural. So there we go. Let's now talk about some properties of these real numbers. Here are the properties that we're going to be talking about today. I have the commutative property. Notice there's not an N in that word. The commutative, like you are commuting to work. The commutative property tells us that if I have these two numbers, A and B, and I add them together, we know that I can switch that order. It doesn't matter when I am adding. It also doesn't matter when I am multiplying. I can multiply my real numbers, A and B, in the reverse order, and everything is still fine. My associative property, note the root word associate in there, associating, being grouped with. This says that if I have some numbers that are being added together, but I have the A and the B grouped together, because I'm adding everywhere, the parentheses actually don't matter, and therefore I can move them. I can add the A and the B first. It also applies to the associative property of multiplication. If I have some numbers being multiplied together, because I am multiplying everywhere, I'm allowed to change how those numbers are associated with each other. I'm allowed to move those parentheses. That's my associative property of addition and of multiplication. Now, my identity property and my inverse property. They're really important when it comes to solving equations. So my identity element of addition is 0. So 0 is very important for addition, and what it tells us is if I have a number and I add 0 to it, nothing changes. This number is allowed to keep its identity. Now, I also could multiply by something and its identity will not change. What number do you think that is? Hopefully you are remembering, I need a 1 there. I need a 1 there. If I multiply by 1, that is my identity element of multiplication. The identity of this number stays the same. Now the inverse property ties very closely with that. The inverse properties say, what if I have this number? I want to add something to this number that gets me back to the identity element of addition, which is 0. And hopefully you're realizing that this is just the opposite of the number. So I'm just going to represent that with -a, the opposite of a. For multiplication, I'm thinking if I have this number, I need to multiply by something that gets me back to the identity element of multiplication, which is 1. And this one we're going to use the reciprocal 1 over a. So I can either turn the fraction upside down, or I can take 1 over the number itself if it's a whole number. The property of closure we don't use exclusively in the real number system, but it's good to know. And all this says is if I take two numbers and I add them together when they are both real numbers, my answer is also going to be a real number. And if I have two numbers and I multiply them together and they're both real numbers, my answer is still a real number. It's just good to have. The imaginary numbers do not have the property of closure. We're not going to work with those today. Now the distributive property doesn't really tie with addition or multiplication individually. It kind of works with both of them. This one says if I have A multiplied by the quantity B plus C, we know how the distributive property works. I'm going to take A and multiply it into both pieces. So I'm going to have A multiplied by B And then I'm going to add to that A multiplied by C. That's my distributive property. We use that with FOIL quite often. Now, let's say I wanted to name the property that was shown. Let's say I had something like -8 plus 8 plus 15, and I see that that simplifies to 0 plus 15. Don't mind my puppy dog, he's trying to help us do math right now. So, when I see this -8 plus 8 becoming 0, I look to my properties up here and I see that happens when I have the inverse of addition. So this is my additive inverse property at work. Okay, let's do another one. Let's say I have 5 times 4 times 13, but the 4 times 13 is in parentheses. But now I know that I could also have the 5 times 4 in parentheses and then multiply by that 13. And the question is, what property is being shown here? And hopefully you can see that this is my associative property of multiplication, because that is the operation I am working with. So this is associative of multiplication. So just naming the property that is C. Now, let's say I wanted to talk about the additive and the multiplicative inverses of a certain number. What if we talk about -5/8? Hopefully you see that my additive inverse is just the opposite. I need to get back to 0, and how I get back to 0 from -5/8 is by adding a positive 5/8. Then when we talk about the multiplicative inverse, I need to multiply by something to get me back to 1. And what do I need to multiply by? Still need a negative, because it needs to be a positive one. Negative times a negative gives me that positive. I need to multiply by the reciprocal. So I have flipped the fraction, -8/5. There we go. So now try this one on your own. What if I ask this same question about the number 3? What is the additive inverse and what is the multiplicative inverse? Hopefully you're thinking my additive inverse is -3, and my multiplicative inverse is 1/3. If I add -3, I get back to 0. If I multiply by 1/3, I get back to 1. Final example I want to go through right now is simplifying just an expression using these properties. Let's talk about 3 times 2q plus r plus 5 times the quantity 4q minus 7r. I don't know these variable values, and that's fine. I just want to simplify the expression. I don't need a final number. I'm allowed to have variables in my answer. So first thing I'm going to do is distribute. So that's my first property that I'm using. Distribute that 3 to the 2q and the r. I get 6q plus 3r. And I'm going to distribute this 5 to both of those pieces. I get a 20q and a -35r. Then I'm going to use my commutative property of addition to move some of these pieces around. Specifically this 3r and this 20q, I'm just going to swap their positions. So I get a 6q plus a 20q plus 3r minus 35r. Just gets my like terms next to each other. Lastly, I'm going to simplify. This isn't really a property we talked about, but we need to do it. Simplifying, I get 26q minus 32r. These are not like terms. I can't do anything more with that, so I am finished with that. There we go, all about real numbers, and we'll talk about this in class soon.